Hello, welcome to New York City Atheists, live on tape, brought to you by New York City Atheists Incorporated. I'm your host, Dennis Horvitz, the David Letterman of the Hopelessly Damned. Today we're going to try to answer a few questions, or at least explore them. Is there life elsewhere in our universe? Sure, if you get there on a Saturday night. But, look, I do this for free, okay? I'm doing this from one of our notorious Sunday brunches, New York City Atheist Sunday brunches. In any case, we're going to try to explore today questions such as how do we define life? What conditions are required for it? Where in our galaxy could life other than on Earth be? Are there other intelligent beings? Are they on their way? We should probably cue the spooky space music right now, but we don't want to pay the royalties. In any case, to answer this question and related questions, our brunch speaker today is Dr. Fred Walter. He is from Berkeley, California, and he is now a professor of astronomy at the Department of Physics and Astronomy at Stony Brook. And in addition to some of the aspects of astronomy and biology, some of the topics perhaps that we will touch upon today is, first of all, the physical conditions of the universe as it exists now, and the age of the Earth. I'm sure that we'll probably get into the young and old Earth creationism and during our question and answer period. And the Drake equation, which is, I guess, the best means so far by which scientists have to estimate the possibility of extraterrestrial life, and I guess that would be intelligent, also including intelligent life elsewhere in the universe. And the information theory. How would we recognize signals from intelligent life on other planets? Well, if they call collect, that would be one way. But, in any case, I'm not the one that's going to be answering this question, so it gives me great pleasure to introduce Dr. Fred Walter.
That means we have about 4 trillion, that's 4 times 10 to the 12th, 4 trillion planets to look at in our galaxy. That's a lot of opportunities for life to get going. And even back in the 15th and 16th century, people understood that. There's about 10 stars born in our galaxy every year. On average, it was more when the galaxy was younger, but it's about 10 a year now. This is a photograph from the Spitzer Space Telescope. Those, the pinkish stuff is dust clouds, and the dust clouds are full of the building blocks of life as we know it. Methane, ammonia, formaldehyde. We have seen organic molecules such as there's a glucose, I believe. Simple amino acids have been found in space and dark in molecular clouds. Chemistry happens. Like it or not, the building blocks of us, the biochemistry, happens in space without need for DNA factory to a living thing to orchestrate it. It just happens. We know that there are planets out there. Here's a photograph of an image of a star. That multicolored speckled thing in the middle is we've thrown away the light from the central star. It's called HR 8799. And there are 3 planets that show up, labeled as A, as B, C, and D. These are planets that are bigger than Jupiter and they're much further away than Jupiter, but there are 3 planets. So here's a star that has planets. Not the kinds of planets we're likely to live life on, but maybe they have things like Europa orbiting them, where we can find life there. We can find extrasolar planets in a number of ways. The 3 most popular are direct imaging, like that previous picture. The Doppler wobble, because when a planet orbits a sun, the star is actually orbiting the planet too, and it moves about. The amount it moves is inversely proportional to the mass ratio. So the star doesn't move by very much, but it moves enough to see. The Jupiter makes the sun wobble by about 10 meters per second. We can detect that on other planets. And transits, if a planet goes in front of a star, we can see that too. Here's an example of Doppler wobble, a star called Gliese 876. This is the velocity, this points at the velocity that the star has in its, when we take a spectrum, as a function of day. This is day of, well, these are Julian days. This is day, and it's moving all over the place. This is in meters per second. So from here to here is nearly a kilometer per second. And if you fit these points, it requires 3 planets orbiting around the Sun. They're 3 fairly massive planets. They're 2.5 times the mass of Jupiter, one just about the mass of Jupiter, and one about 7.5 times the mass of the Earth. So they're 3 fairly massive planets orbiting this fairly small star, actually. Down in the lower right is an artist's conception of at least 2 of those planets. But we can we've looked at a lot of stars. Over 300 stars now have planets. Most have been found by this technique. They don't all have 3 planets. Most have just 1. Transits we see when the star goes in front, a planet goes in front of a star, the artist's conception is on the left. It does happen in real life. On the right is a picture of Venus transiting the Earth back in 2004. If you missed it, it will happen again in 2012. It will not happen again for another 108 years. So catch it in 2012. Okay? It happens every 8 years, and it doesn't take over a century off. Now, if you are not at the Earth, but if you're out at Alpha Centauri or someplace looking back, the relative sizes of Venus and the Sun are the same. Venus is blocking about 1%, about 1/10% of the light of the Sun. It doesn't matter whether you're on the Earth looking at it and Alpha Centauri looking at it. You can see it. And we have a spacecraft mission called Kepler that is out there now looking at 100,000 stars in the constellation of Cygnus, looking for these kinds of transits, looking for very small diminutions of light due to a planetary transit. Jupiter blocks about 2% of the light of the Sun, if you see it from a great distance. That's easy to do. That can be done, you can do that in your backyard with an 8-inch telescope. People do it. It's hard to see a planet directly, to take a direct image, because planets are so faint. This is just a plot that shows the brightness of the Sun and the brightness of the planets, and this is reflected sunlight. This is logarithmic. From here to here is a factor of 1 billion. 1 billion, 1 with 9 zeros. What's happening out here is Jupiter is hot because Jupiter is still contracting a little bit. It's got some leftover energy from 4 billion years ago, so it gets brighter. But planets are faint, they're hard to see. But we've now seen, here's a direct image of the second planet, second star that has a planet. It's Fomalhaut, which is a fairly bright star, one of the 10 brightest stars in the sky. It's in the southern hemisphere, you can't see it from here. And this right here is the planet. It's been seen on 2 occasions, and it's moving. In 2 years, it moves this far. We can say it takes about 100 years to go all the way around the star. We can make an estimate. It's a number of Jovian masses. It's a big planet far, far away from the star. When we're looking for planets, one thing to keep in mind is it's hard to find the Earth. The Earth is small. It's not bright. It's easy to find giant planets like Jupiter or bigger than Jupiter. By definition, a planet goes up to 13 times the mass of Jupiter. Above that, it's a brown dwarf, but that's another issue. What we can see are these super Jupiters, these very massive planets orbiting close into the star. This is the mass of the planet plotted versus the distance away from the star. These green dots, Venus, Earth, Mars is down here, Jupiter, Saturn, Uranus, Neptune. This box is basically where we're currently sensitive to planets. We could see Jupiter at 5 astronomical units from the Sun if we were out at some other star looking back. We cannot see the Earth yet. This is what the Kepler mission is going to see. It'll see Earth if there are Earth-like planets around other stars, at least the ones we look at, as it transits in front. But it's hard to see small planets close in. It's easy to see the large planets. So we have a very biased view of what's out there. Nonetheless, we can say that at least roughly about 10% of all solar-like stars have at least giant planets. They don't look like the solar system, because the giant planets are close to the star, not far away. But planets are not rare. Which is good. If you're interested in finding intelligent life in the universe, they need a planet. So, SETI, last topic, the search for life, search for extraterrestrial intelligence. That's what we think we're looking for. Yeah. Robots, Klingons, life as we don't know it. It's hard to read. I know perfectly well that at this moment the whole universe is listening to us, and that every word we say echoes to the remotest star. Another quote from the Man, Woman of Shiloh. It seems appropriate for SETI. Those are photographs of 3 radio telescopes and some planets and the moon in the background. How do we communicate? Okay, we're not going to be able to go to the nearest star and find its planets the way we go to Mars. Certainly not in our lifetimes, not for the foreseeable future, because the universe is so damn large. So how do we communicate? We're going to have to do it by radio, by laser, by electromagnetic radiation somehow. How do you communicate? This is the information theory part of the talk. I'll go through it a little quickly. Pictures worth 1,000 words, right? Picture is the way to go. You start sending bits of information. How do you interpret it? 2 dimensions are better than 1. If you send a string of n bits of information, if n is a composite number made up of 2 primes, there's only 2 ways to arrange that into a picture, n by x by y times y, or y times x. And you can, as an example, this is a simple message. You can write down these numbers if you want and do this yourself. But there are 115 bits here, and 115 is composed of 2 prime numbers, 5 and 23. So I can make an image that's 5 by 23 or 23 by 5. And you can do it 2 ways. One way makes sense, the other one doesn't. And I give this as a question when I teach this course, Astronomy 248, the Search for Life in the Universe. I give them those 115 bits and I tell them to decode it. And I don't care what they come up with. The answer, the question is, are the aliens friendly? And, well, actually, either yes or no might work. We don't know why you're saying hello. Here's a real signal that was actually sent in 1974 from the Arecibo radio telescope. So it's a globular cluster, LM13. It was sort of a commissioning test. We don't expect the signal back because it'll take about 30,000 years for the signal to come back if they hear it and respond. And it's not the best place to look for planets for astrophysical reasons. But this is the message that was sent. This is the picture. It's like 1,500 or so bits of information, and when you organize it, it looks like this. The colors are artificial. They're ons and offs, okay? And the colors are there to help you see that there are different parts. And how do you interpret a signal like this? Well, you got to be a little bit intelligent to interpret this. So presumably, if you can build a radio telescope and receive the signal, you can respond back because you can interpret it. And what you do is you start by counting. This is 1, binary. 0, 1 is 2, 1, 1 is 3, 0, 0, 1 is 4, 1, 0, 1 is 5. So that's the numbers 1 through 10 in binary. And below that is gives another series of numbers. Those numbers are 1, 6, 7, 8, 15. That's supposed to tell the biochemists who are listening that we are made of elements 1, 6, 7, 8, and 15. That's hydrogen, carbon, nitrogen, oxygen, and phosphorus. Okay? Now, it may take a while to come to that realization. That's what we're trying to say, but that's what you're trying to say. What follows are the molecules of DNA. Again, is in terms of atomic numbers. I used to know how to interpret that, but I can't anymore. What follows that is a representation of the double helix for DNA. If it's life as we know it, they're using DNA. If it's not life as we know it, they may look at this and say, I don't know what's going on. Maybe they throw up their hands if they have hands. Well, who knows? That number in the middle says how many nucleotides are in a typical DNA for a human being. It's a large number. So I guess we're telling them how complex we are. What follows that is a representation of a human being. I don't know how some alien would interpret that, but it's supposed to be interpreted as this is a human being. On the left is a representation, shows the height, and that's in a fraction. This was radio wave was sent out with a wavelength of 21 centimeters, so all the units are in units of 21 centimeters, so that's your height in units of 21 centimeters on the left, and on the right is a number giving the total number of total population of the Earth. It's a very large number as of 1974. Below that it shows the solar system, or at least it's supposed to be interpreted as the solar system. The big thing is the sun. The planet that's out of line is where we're from. It's different. So Mercury, Venus, Earth, Mars, Jupiter, and Saturn are big. So these are little planets, giant planets, medium-sized planets. And on the bottom is a picture of a radio telescope. There's an awful lot of information that's encoded in this very simple picture. It's not something that you can, if you don't have an easy basis to interpret it, it's going to take you a while to figure it out. But you can figure it out. At least if you're an intelligent alien, the hope is you can figure it out. So that's how we want to do communications, and maybe someday we'll get a signal back if they're out there. Okay, so this is the one equation. This is the Drake equation. There is no answer to the Drake equation. The Drake equation has been called by one of my colleagues the biggest, well, he calls it bogus. It's one of the, all astronomy textbooks have this, and it's an equation that has no answer. It's designed to let us formulate the questions properly. And we want to figure out how many planets, how many intelligent civilizations are out there. We want to be able to focus in on what are the important factors. Well, the important factors are encompassed in this equation. The factor n is the number of civilizations in the galaxy that are capable of interstellar communication. That's what we're interested in. How many can talk back to us? That's that n. We're going to get n by multiplying a whole bunch of probabilities together. If n star is the number of stars in the galaxy, we're going to exclude the possibility that life exists between the stars. It needs to be near a star, we need energy in it. Okay. So we're going to start with the stars. There's 400 billion stars. Well, some fraction of those stars have planets. Could be 100%. It's at least 7%. So that's a number. It could be less than 1. So the 400 billion can come down a little bit. Then some fraction of those stars, I can make a more complicated equation. Some fraction of those stars are just not good candidates because they're too hot or they're too cold or what have you. But we'll leave that for now. How many habitable planets are there per star? In the case of our solar system, 3. There are 3 potentially habitable planets. More if you include, say, Titan and Europa. Then you have to multiply that by what fraction of those planets life actually evolves. There was at least one planet in our solar system. Could have been more, we don't know. Some cynics would say it's 0 on average. But it's at least 1 in our case. Then the fraction of those planets where life evolved, where intelligent life developed. Well, that could be a large number, it could be 1, it could be a small number, it could be close to 0. On our planet, life was very happy being unicellular for 3 billion years. Something happened 500 million years ago to make life evolve from basically blue-green algae to us. It was very happy for a while, but some stress happened. I think it was a Snowball Earth episode that made it adapt in a way that became multicellular. Once it became multicellular, there were lots of more opportunities to evolve. So it could be that life is very happy staying single-celled for a long period of time. It did on the Earth. It could be single-celled bacteria are common everywhere, and we're the exception. That's an unknown factor, but that's a factor you have to consider. But suppose you do have intelligent life developing, how much of it becomes technologically capable? Maybe it gets stuck in the Stone Age. Maybe it's dolphins, which could be intelligent, but they're not going to build radios ever because they don't have hands. How's a dolphin going to build a radio and communicate? People think they're intelligent. They can't communicate over interstellar distances without a radio. And then it all depends on the lifetime of the civilization. They're not going to broadcast forever. Maybe they kill themselves off after 100 years. We've been close to doing that for a while. Maybe they become uninterested in chatting. They go through their Twitter and Facebook phase and they turn off. You multiply all these things together, you get a number. And you can manipulate these. You write down your best guesses. This is designed to focus your attention on what are the important parameters. What do we know? What don't we know? We know some of the astrophysical laws. We know the number of stars. We know the number of fractionally planets, sort of planets per star that are habitable. We think we know where does life develop. I would say that's probably 100%. But below that, we know absolutely nothing about what makes life develop into develop intelligence, and then become technologically adept and all of that. So you can put in any numbers you want, and I guarantee you can find some combination numbers that will come up to 42 for the number of intelligent civilizations in the universe. And if you enter the galaxy as a whole, you multiply by another 400 billion, because that's the number of galaxies in the universe that we know. So the question is, if you're an optimist and you think there are lots of intelligent civilizations out there, the question is, where are they? This is the Fermi paradox, because Fermi understood that if there are intelligent civilizations out there that want to communicate, they will have done so by now. All you need is a von Neumann probe. What's a von Neumann probe? It's basically a self-replicating spacecraft. We can probably build one in a few tens or hundreds of years. You launch one, it goes to some planet, builds copies of itself, sends them out to other planets. You set up more than once, you go in 2 or 4 directions. So you're not doing it by sending people out, you're doing it by sending these robots out, but they're self-replicating, they build copies, send them more out. So after a little bit of time, you have one probe for every star in the galaxy, or more than one. If you can travel at 1/10 of the speed of light, and that's in principle doable by technology that we think we understand, you can explore every single planet in the galaxy in 1,000,000 years. 1,000,000 years is no time at all compared to the lifetime of our planet, the lifetime of our galaxy. 1,000,000 years, the lifetime of the galaxy is 10 billion years. 1,000,000 years is nothing. Well, we have no evidence that anybody's visited us. Maybe they're hiding. But so the question is, where are they? One possibility is we're the first civilization to come of age in the galaxy. Statistically unlikely. Could be we're the only civilization in the galaxy. That's probably a higher probability. It could be there's other people out there and they're hiding from us, or they want us to develop on our own, which I believe is much more probable than UFO stories, that they're actually visiting us and meddling with us. But there are a number of possibilities that we don't know what the answer is. The question is very profound. The most profound questions are the simplest ones. Where are they? And you have to think a lot about the right answer. I think we're probably the only intelligent civilization in the galaxy at the current time. I think there's a lot of life out there, but I don't think there's anybody else out there who can talk to us. And that leads up to the rare Earth hypothesis. And I apologize, this is somewhat hard to read. This has been put forward by Ward and Brownlee at University of Washington. The Earth may actually be quite rare, planets like the Earth. There are a number of special things that happen here. For one thing, we're the right distance from the center of the galaxy. There are, you can ask questions later, but closer to the center of the galaxy, further away from the center of the galaxy, are less conducive to life as we know it. There is a galactic habitable zone. The solar system is just the right metallicity. It's not too much iron, not too little iron. You get different kinds of planets if you have too much iron or too little iron. The sun is rather peculiar, actually, for its age. It doesn't flare as much as it should. That's good for life as we know it. The Earth is at just the right place in the habitable zone, because the habitable zone changes with time. The sun is getting brighter, the habitable zone is moving out. The sun started at one end, it's moving to the other. In 1 billion years, well before the sun burns out, the Earth will become uninhabitable because all the water will evaporate. The surface temperature will go above the boiling point of water. Nothing we can do about it, except unless we can move the planet. And maybe in 1 billion years we'll know how to do it. The moon is unusual. The moon is large compared to the planet, but the moon stabilizes the Earth's rotation. Planets flip over. Mars flips over. It has a very unstable climate. The Earth has a very stable climate because the moon stabilizes the Earth's rotational axis. It keeps it pointed basically in one direction. The Earth is tectonically active. That means the atmosphere gets recycled. If the atmosphere doesn't get recycled, you end up like Venus, you have a runaway greenhouse. That hasn't happened yet. It may happen someday, but the Earth is still tectonically active because it's the right mass. Too little mass, a few percent matters. Venus is only about 5% less massive than the Earth. Jupiter has protected us. Having a massive planet far out protects us by ejecting a lot of the cometary material that falls into the inner solar system, protecting against impacts. Impacts are not good for life as we know it. And of the 358 known planetary systems, most have hot Jupiters very close to the sun. We don't have that. We think the only way you get a hot Jupiter close to the sun is by forming it out where Jupiter is today and having it migrate in. And if it does that, it pushes everything in front of it, and any terrestrial planets would fall into the star. We don't have a hot Jupiter. We're lucky. The Earth has not fallen into the sun. So you can make arguments like this and argue that the Earth is really peculiar. This is the Goldilocks problem. The Earth is just right. That's why we're here. It's going to be hard to find another planet just like this anywhere in the universe. So, I hope I've given you a lot to think about. But it can be summed up very nicely in this old Pogo cartoon where this character, I forget the name of that character, but he says, I've been reading about how maybe there's planets peopled by folks with advanced brains. What was that, huh? On the other hand, maybe we got the most brains. Maybe our intellect is the universe's most advanced. Either way, it's a mighty sobering thought.